All right, this is the last section of chapter 5, naming acids and then figuring out formulas for acids. My little room where I normally record these is really, really hot, over 90 degrees in there, so I moved outside. So if you hear some background noises, some birds chirping, some ducks or chickens making noise, that's why you're hearing that, some traffic noise as well. So an acid is anything that can donate a hydrogen ion, so H positive ion right there when you dissolve it in water. Most acids are actually white solids and they do not become an acid until you dissolve it in water. You can recognize an acid because the hydrogen is always going to be written first. And a molecule with one or more H positive ions attached to an anion technically then would be an acid. And really, it would almost be more of a formula unit because it is an ionic compound, not a molecular compound. There are two different types of acids, those that contain oxygen, those that do not contain oxygen. So if it contains oxygen, it's called an oxyacid. If it does not contain oxygen, then you use the prefix hydro. You never ever use the prefix hydro if the anion, the negative ion, the second thing listed, contains oxygen, and then you change the ending or the suffix to IC. If it's an element, which most of these acids are going to be hydrogen with a halogen and to an extent chalcogens, water, H2O, technically it can be an acid or a base, and that is a special name. It's called amphoteric. So it goes back to the root element name. So HCl, hydrochloric acid. Hydro meaning that it does not contain water. Chlorine becomes chloric, and then you always tack on the name acid. The only polyatomic ion that does not contain oxygen that forms an acid is cyanide. So this would be called hydrocyanic acid. H2S, so sulfur right underneath the oxygen on the periodic table, also a chalcogen, would be hydrosulfuric acid. When the anion contains oxygen, it's going to contain a polyatomic ion. You have to look at the ending of the polyatomic ion in order to figure out how to name it. And this is why I like to cover the stock system before I cover naming acids, because you follow the exact same pattern. It's going to become either ick or aus, just like iron became ferric or ferrous. Well, just like with the stock system, the one that had the lower oxidation state was OUS, the one with the higher oxidation state was IC. The acid with fewer oxygens is called OUS. So if you have the sulfite polyatomic ion, it's going to become sulfurous acid. It goes back to the root element sulfur. It does not, you don't just drop off sulfite and make it sulfus. It's sulfurous. It's not phosphorus acid, it's phosphorus acid. The one that has more oxygens, so SO3 is sulfite, SO4 is sulfate, would be called sulfuric acid. So H2SO4 is sulfuric acid, H3PO4. Notice it goes back to phosphorus, phosphoric acid. Acetate, C2H3O2. So it really doesn't go back to a root element here because it is a charged molecule, the acetate polyatomic ion. Acetic acid, commonly known as vinegar. A solution of roughly 5% acetic acid is what is known as vinegar. Here's a mnemonic device which I put on your note sheet as well for naming acids that I came up with. I ate it and it was icky. So if your polyatomic ion ends in ate, it becomes ick. If it ends in ite, it becomes aus. So I ate it and it was icky, took a bite and it was lousy. So here are some common acids that do not contain oxygen. So you can see we have HF is hydrofluoric acid. Interesting thing with hydrofluoric acid, it eats glass. So you can actually use that in craft projects to etch glass. HCl, probably the most common acid that's around, hydrochloric acid. HBr, hydrobromic, hydroiodic, hydrocyanic, hydrosulfuric. Notice they don't contain oxygen, so you use the prefix hydro. If it does contain oxygen, then again, you have to go back to the polyatomic ion. This is nitrate, so it becomes nitric acid. Notice no hydro because hydro means it does not contain oxygen. This does contain oxygen. NO2 is nitrite, so it's nitrous acid. sulfuric acid, sulfur-us acid. And if we notice on the slide a slide or two ago, we also had hydrosulfuric acid, which is H2S. Three different acids, three completely different compounds. They are not interchangeable. Phosphoric acid would be known as a triprotic acid because we have three hydrogens here, whereas sulfurous and sulfuric would be diprotic acids because you have two acidic protons here, H2, H2, H3. You would think this is a really strong acid, but it's actually a really weak acid. Now, just because it's a weak acid doesn't mean that it can't do as much work or damage as a strong acid. It just means that it stays mostly as H3PO4. If you ever get a chance to look at swimming pool chemistry, it's all based on the pH, and different chlorines and different hydrogens will break apart off of the compound at different acidities or pH levels. And then, of course, we have acetic acid. Phosphoric acid you find in caramel colored pop like Pepsi, Coke, RC. A really nice flowchart for naming acids. Does the anion contain oxygen? If it's no, you use hydro, the anion root, and then you change it to ic. So for instance, bromine becomes hydrobromic acid. If it's yes, check the ending of the anion. If it ends in ite, it becomes aus. Sulfite, phosphite, nitrite becomes ous, and it goes back to the root element. And I ate it and it was icky, so sulfate, nitrate, phosphate would become ic. Writing the formulas of an acid is even easier than figuring out the names of the acid, because whatever the charge on the anion is, and remember anions always make the same charge, that's how many hydrogens you need. So for instance, hydrobromic acid, it does not contain oxygen. So that's why it has the prefix hydro. So bromic means it comes from bromine. Well, bromine, group 17, a halogen, has a 1- charge. Hydrogen only has one electron that it can give. So therefore, we need one hydrogen to go along with it, so it becomes HBr. On the other hand, carbonic acid. An interesting thing with carbonic acid is this is actually the primary buffer system of your blood. As you exercise, you produce lactic acid. As it gets out of your muscles into your bloodstream, the pH of your blood starts dropping. One of the ways that your body controls the acidity of your blood is by your breathing. You exhale more carbon dioxide. When you exhale more carbon dioxide, it dissociates the carbonic acid back into ultimately water and carbon dioxide. So carbonic acid, very, very interesting. It's a very weak acid as well. So that's also what happens when you carbonate pop water to make seltzer water. Anything carbonated, a small amount of CO2 reacts with the water molecules to produce H2CO3. So carbonic comes from the carbonate polyatomic ion, CO3. Since it has a 2- charge, we need a 2+ charge is to cancel it out or to transfer the electrons. So carbonic is H2CO3.